Okay, this is screencast 5 for Business Administration 571, week 5. And I have a correction. If you'll notice here, let's see if I can get this thing to start drawing. This should be 0.00135, and this is 00135, and then when you add them up, you do indeed get 0027. So, where were we? Well, as you know from your review problems in Ryan's Chapter 3, if we are counting the number of non-conforming units in each batch of n units built, then the probability distribution of this count metric is binomial, and it has the parameters n and p, where p is the probability of making a non-conforming unit, called the probability of success, where in this case success is actually the failure to make a good unit. So we want to come up with control limits, upper and lower, such that our false positive rate is about equal to what an X bar chart false positive rate is. Why? Because the culture that we have been bringing into our firm about quality depends on a large part on the use of control charts, and the only way we've been able to convince senior management to allow control charts to be run in stage 2 and have management authority to shut down the line when and if a signal is received is to have convinced them that these charts will rarely give false positives. And in fact, we've educated senior management to the fact that if we use plus minus 3 sigma X bar control limits, then the false positive rate, assuming normality is holding for the X bar values, the false positive rate will be a tiny number, 0.27%. So we want to use an NP chart with the same amount of management blessing. So what we need to do is engineer the control limit so that the false positive rate on the NP chart is about the same as the false positive rate on an X bar chart, so that management doesn't think we're doing something which is unreliable. So I've written out here the two probabilities that make up the false positive rate always in any chart. The probability that the plotted metric is below the lower control limit even though nothing has changed, i.e. P has not changed. We want that to be about 00135, and we want the probability that X will stray above the upper control limit. We want that to be 00135 also, because when we add up those two tail probabilities, as they're called, we want to get the total probability of either straying above or below. We want that probability to be the magic 0027 that is the false positive rate of an X bar chart. We have a challenge, though, and the challenge is the probability mass function or the PMF of a binomial is, for P much less than 0.1, which is what you want it to be. In our example, so I'll say in the example, P hat is 0.02. Well, the probability mass function tells us the probability of getting some number of successes in a batch of size n. So we can plot the probability of one success or one bad unit in the n units, and we can plot the probability of having no bad units, or 2 bad units, 3 bad units. In our example, this goes up to 100. Here's 99. If P is about 0.02, we would not expect to see a large number of bad units. Now, the expected value, oh, and by the way, I have this wrong. This is, remember we have a workforce of 1,500 people. So what's the expected value of X? Well, we all know from reading our Ryan that that's N times P. So what is it for our example? 1,500 times 0.02. Well, 20% of 1,500 is 300. So I guess that's 30. So out of 1,500 paychecks, if the probability of a check having one or more audit exceptions is 2%, then you would expect to see, on average, for a typical pay period, you'd expect to see about 30 paychecks having mistakes on them. So what would the bars corresponding to the probabilities look like? I ought to really make this a lowercase x. So this is a PMF right here. It's just a bar chart of the probabilities of getting a particular number of successes. Well, if you've got a real low probability of success, you're going to see a picture that looks kind of like this. So here's 30, and here, way out here, is the number 1,500. You know, so there's lots and lots of space between 30 and 1,500, and most of the probability spikes are centered around 30, which is the expected number of bad units. Well, our task then is to find two numbers here and here. This will be the lower control limit, and this will be the upper control limit, such that when you add up these spikes, you add up spikes, you get about 0.00135. And down here, if you add up these spikes, you also get 0.00135. But there's no table that tabulates every single binomial distribution, because as soon as you change P or you change N, this plot changes. So basically you have to find these numbers through trial and error. Ryan spends a lot of time in his book on normal approximations to the control limits for an NP chart. If you're doing a handwritten exam, you can be asked by somebody to use the formulas in Ryan to find the control limits. But if you're going to do real work, you want to use the trial and error method, because that will give you what are called probability limits. and that's what is going to give you the most accurate false positive rate to the one that you want. Now, if you're going to add up spikes, you're going to have to accept the possibility that because these are discrete jumps in probability, you may not be able to find a magic number that gives you exactly 0.00135. And the same goes for down here. So you're going to have to find the closest ones to give you a probability in the upper tail and a probability in the lower tail that is about 0.00135. So for this example, I ran the numbers in Minitab a long time ago, and you would get the same result if you ran this in SAS. And you get this output. Between 14 and 15, you get the probability of 0.0008 and 0.0018. So the probability that X is less than or equal to 14 bad units in a batch of 1,500, if P is 0.02, is 0.308. You go up to 14 paychecks that have mistakes in them, and the probability of seeing 15 or less is 0.0018. Well, 0.00135 is in between these two numbers. So if you want to be conservative and have your chart be a little more sensitive to a problem, a shift in P, you want to go with this little higher number. But you see, there's no way you're going to get to 0.00135 because the distribution is discrete. Nobody's ever seen 14.7 paychecks that have one or more audit exceptions in them. Either they see 14 paychecks or 15 paychecks. At the other end, we have the same problem. With 46, we get 9978, and at 47, we get 0.9987. Well, 1 minus 0.99865 equals 0.00135. So the magic number we're looking for in this CDF, so these are CDF values, the magic number that we would like to be able to acquire is 99865. The best we can do is 9978 or 9987. Well, clearly this number is closer to the 9987, so we're going to run with the 47. So this is going to be our lower control limit, and this is going to be our upper control limit. So if we see 15 or fewer paychecks that have no audit exceptions, rather that have audit exceptions, then we're going to declare that there is a shift in the probability of making a paycheck with audit exceptions, and in fact it's gone down. So that might mean that without authorization, payroll has farmed out the activity of computing paychecks to an outside firm that never makes any mistakes. However, this outside firm is sharing this sensitive payroll data with advertisers. And you pick it up on your chart because all of a sudden payroll has gotten a lot better at their job. Or, the more likely event, you see a month where there are 49 paychecks that have one or more audit exceptions in them. That's exceeding the upper control limit, and you declare a signal. And then you march into payroll and you say, okay, there's something wrong here. Before you were running at 2% error rate, now it's higher, and statistically it's higher. statistically significantly higher. So we've got to find what went wrong. Of course, the manager of payroll is going to complain bitterly that you're interfering with their operation, but you've got the VP of finance standing next to you. And the VP says, no, this control chart was authorized by senior management, so we are going to look around. We're going to look at your operation and try to figure out what went wrong, because something has gone wrong. And now this manager knows that his boss is talking to him, or her boss. So things happen. So the chart of before has an upper limit of 47 and a lower limit of 15. Okay, we have an issue. Oh behold, whoa, can't let this opportunity go. So here's a lecture question, and that is, how would you modify the SAS file on my G drive of the name npchart.sas so that you can run the audit exception data that I've put down in, I guess I put it in the last screencast. So I gave the data in the last screencast, and the question is, how would you modify npchart.sas in order to run that data in SAS and build an NP chart? So that's my question, lecture question. Okay, so issue. Well, as quality improves, the rate of mistakes, for example, making non-conforming units, goes down. Why is the semiconductor industry so interested? Well, why does this happen? This happens because as you clean up problems, you slowly ferret out things that you've been doing that are causing mistakes to be made or manufacturing processes to fail. Well, the result is any NP chart is having its P probability of a non-conforming unit go down. Maybe P is now much, much less than 0.1. So I was talking about the semiconductor industry just a minute ago, and asking why does that industry have such an interest in quality tools such as control charts. The answer is you can almost never make a bad chip, a computer chip for a phone or a computer, either the CPU, the central processing unit, or say a memory chip or a graphics handler chip. And if you notice with the global presence of microchips now in all sorts of devices, it is very seldom that these chips break. Other things break long before the electronics, the actual microchips, fail. And And you almost never acquire a phone that has already in it a broken chip. So the failure rate, or the probability of making a non-conforming memory chip, must be essentially zero. Well, it's a manufacturing process. How can it be so good? That industry knows that their mistake rate has to be almost non-existent. But this causes a problem with monitoring. And the problem is, well, if I'm going to monitor a process that has a very low failure rate, in this case, the LCL will be essentially zero, because that's going to be because the probability that x is less than or equal to 1 is going to be actually higher than p, unless n is very big. Take as an example p equaling 0.001. You've managed to get the non-conforming unit probability cranked all the way down to 0.1%. Let's say your n is equal to 100. Then NP is 0.1. 0.1. That means you, in every batch of n units, you expect 0.1 units to be non-conforming. I still got it wrong. Non-conforming. How embarrassing. My point is, you're going to watch that line a whole lot before you ever see a 0.1 unit. In other words, you'll never get a event below the lower control limit. So the lower control limit, the LCL, will be 0. So the lower control limit is useless when p is really small, but that's where you want to go. So you have an alternative. In this case, use the number of units before a non-conforming unit is built. As your metric. So what you're going to do is say, here is x, and this is minutes, or some sort of time unit. And what you do is you monitor how many minutes go by before you get a non-conforming unit. So x equals the number of units before a non-conforming unit. So let's say p is really small. You would expect x to get big as p gets small, goes towards 0. Remember, p can't get below 0. So as the probability of making a bad unit goes down, you will make many, many units before you make a bad unit. So you make a bad unit, and then you start the counter again. You make a bad unit, and then you start it again, and you start counting the number of units that go by that are good until the next one. So you can come up with control limits. Now, your excursions into loss of quality no, this is improvement in quality. See, P going down means quality is improving. But on an NP chart, x equals number of bad units. With your control limits, going this way means improvement in quality. So I'm switching things around from what Schuhart was focused on. Schuhart was focused on watching for loss of quality. But modern thinking is you should be monitoring for when you get improvements in quality. And the problem with an NP chart, when you use it to monitor improvements in quality, is that it's got a hard lower limit of 0 that it can never get past, because it's 0. You'll never make fewer than 0 bad units in a batch. But if you monitor the number of units that go by before you make a bad unit, then improvements in quality, there's lots of room to see improvements, because improvements mean that this value will get larger and larger, and there's no limit on the direction of going large. End of screencast.